So today we'll discuss still perturbation theory, still the time-independent case, but I will illustrate the case where you have degenerate levels. Okay? So this will be useful in certain applications, for instance, calculating perturbations of the hydrogen atom spectrum and so on. Okay, the problem is the following. Suppose that a certain eigenvalue, n, E0n, is really degenerate. Let's call the degeneracy Dn. Okay? So it could be any number greater than 1. It means that your H0, okay, matrix, will have some eigenvalues in the diagonal here, but when you come to En, you will have several of them. Okay? All the same. And the dimension of this block is dn by dn. Okay? For instance, in hydrogen, not counting spin, the ground state is non-degenerate. The first excited state is fourfold degenerate, S and 3p. Okay? If you count spin, it's 8 states that you have. You go on and you have 9 times 2, 18 states. Okay? So all these have exactly the same energy, and therefore when you represent in a matrix form, there would be a block with several states exactly identical. To distinguish the different states, therefore, we will denote them by, for instance, some index alpha. Okay? So alpha here for a given n goes from 1 to dn. Okay? But you realize that the choice of this thing is highly arbitrary. Because if you mix them by a unitary matrix, so suppose that rather than, for instance, let's be definite. This is the 1s, this is the 2s, and the 2p. Okay? These four are degenerate. You can mix them by any linear combination which is unitary. So, for instance, you can define new vectors, okay, such that let me denote them by a prime, okay, which are essentially the old ones, n alpha prime summed over alpha prime, okay? And this matrix here you select to be unitary, okay? So it's a kind of rotation in this degenerate state. Now you know that rotation doesn't change the identity, for instance, okay? Something that is equal to the identity will remain equal to the identity. Now, this is not the identity, but almost, okay? This is equal to E0n times an identity block, okay? dn by dn, okay? So, in this new basis, where this is a unitary rotation, the matrix will be exactly the same, okay? So you realize that you can mix, you can make combinations of 2p, 1, 0, minus 1. For instance, you could use Cartesian 2p states, okay, rather than the spherical ones, okay? You remember the p, x, py, and pz. Those are combinations of the p plus 1, minus 1, and 0. Doesn't matter. The energy is exactly the same at this level, okay? So the question rises, which ones are the best to use? After all, there is this freedom, but maybe the freedom ends once I introduce some perturbation. Let's see. So the problem is the following now. I have now not only H0, I also have the perturbation for the matrix for V. Okay? Let us concentrate on the same object here. Okay? On the same subspace, dn by dn. This will be full of numbers, obviously, in general. Okay? And I ask you, okay, what do you think will be the best choice for the state to use here? Okay? This is the question. I will prove for you that the best choice is make a linear combination of only those states. Obviously, I'm not asking you to combine everything. Okay? Just those things. I want to do the word is here. The word is in a box, dn by dn. Okay? Nothing else. Only those states are considered. Okay? You can find a unitary matrix such that the perturbation is diagonalized, okay, because you know that you can always diagonalize an Hermitian matrix. V is Hermitian, so you can find a combination of the old states such that V is diagonal in this new basis. Okay? You realize you can always do this because this is a finite dimensional matrix, and you can diagonalize it by some unitary rotation. All right? So there is, in this big freedom, a particular choice that is particularly useful, apparently. Okay? And it's the one in which V, in this subspace, obviously, is purely diagonal. Okay? Let's see, and I will prove to you that this is indeed the best thing you can do. Okay? Is this clear to everybody? Okay? So I'm using the freedom on the U to restrict myself to this little problem, dn by dn, and tell that the states that are better, that are best in absolute terms, are the ones that diagonalize the perturbation in that small subspace. Now, let's see why. So let us denote by without the thing, the good states. Okay. So I put here the prime is for the odd ones, and the good one will be without prime. Okay. Now, I know that I would like to have an expansion, for instance, for the eigenvalues, which is of this form, E0n plus some lambda E1 and alpha plus, okay? This is the usual expansion we wrote the first time, okay? Similarly, the states, I would like to have the unperturbed one, okay, suitably chosen. There is some freedom on this, and I will prove that the best you can do is indeed this, okay, plus some lambda phi1 and alpha plus, okay? This is the general thing we have in mind, expanding. And in some sense, we want that when lambda goes to 0, not only the energy goes to this, but the state goes to that. All right? So this is the smoothest, the most continuous thing. You want that the state goes to this object when you have a lambda which is finite and you reduce it to 0. And this is, in some sense, without any lambda, without any perturbation, you really don't know what states to use, right? But if you let yourself be guided by the perturbation, so you turn on a small lambda, then maybe the system will tell you, okay, choose this, because in the limit lambda going to 0, I will reach some state. And I will show that this is the right thing to do. Okay, So let us write now the usual H0 plus lambda V times the state, so times phi0 and alpha plus lambda phi1 and alpha plus blah, 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 okay, equal to energy, so E0 n plus lambda E1 and alpha plus blah, blah, blah times phi 0 n plus lambda phi 1 n plus etc. Okay? So I want now to extract again the terms of, yeah.
Why there is not alpha in the image of untouchable?
Where?
In the image of untouchable plutonium.
Because I told you that they are degenerate. So there is no alpha there. They don't depend on that. Look at there. I add an index alpha, which runs from 1 to the n to distinguish several states with the same energy. All right? In other words, there is no need for an extra index there. They are exactly the same.
But why for the bigger state?
Because there are several states with the same energy. Suppose that you have an energy, 3, and there are 7 states with the same energy, 3. Okay? 3 is 3. But then you have state number 1, number 2, number 3, number 4, number 5, number 6, and number 7. Okay? And this is the alpha that distinguishes the states. The energy is the same, however. Okay? You see, it's the same number here. No need to put alpha. So there is no alpha there. In general, there is an alpha there, everywhere. All right? So let us proceed to first order. To first order, I have this, and on this side, I have this, okay? And I have this. Okay, so let us collect everything. I will do it down here. The equation that you end up writing is H0 minus E0n phi 1 n alpha plus V minus E1 n alpha phi 0 n alpha should be equal to 0. Okay? These 4 terms I reassembled like this. Okay? So I brought E0 here with a minus sign, and I brought E1, you see, here with a minus sign, and I got rid of lambda, which is just to the first power in every term. Okay? This is exactly the equation we wrote last time. Exactly. Simply now I have an extra index alpha. If you check when we did the non-degenerate case, I didn't have an index alpha. Now I have. Okay. So what do? Well, same trick as last time. So let me take now the matrix element of this with a state phi 0 n alpha prime. Any state in that same subspace. Okay? So n is the same. Alpha prime might be different. Now, since the energy of all these states is H0, you see that again this term cancels. Okay? However, here now I have plus phi 0 n alpha prime. Okay? So what I conclude is that the matrix element of V between the two states phi 0 n alpha and phi 0 n alpha prime, okay, must be exactly equal to E1 n alpha times the overlap between the two states. But you know these two states are orthogonal. So delta alpha prime. So this is the crucial thing. You see, a delta appears. What does it mean? It means that in order for all we wrote to be meaningful, the matrix element of V must be diagonal. Okay? So you realize now that this phi 0 n alpha was not any arbitrary choice, was actually the right one suggested by V. So V is like a hint. Please find the combinations that diagonalize me. Okay? And these are your phi 0 n alpha. Okay? Is this clear to everybody? It looks like, a trick. It's not a trick. Okay? It is behind my way of writing this expression, pretending that this is perfectly smooth all the way from lambda finite towards lambda equal to 0. Okay? So if I do have different states as a choice, the thing will not be continuous, in other words. Okay? You choose the state in any way you want, but the perturbation, okay, tells you that they want some states. When you take lambda going to 0, what you get is different from what you chose by chance. Okay? So in some sense, the perturbation tells, please select the ones that diagonalize me, and if you select others, the process would not be smooth. Okay? And you would not essentially be entitled to write something like this. Okay. So hopefully you understood that what you have to do. So the first order corrections are what appears here. Okay? Once you diagonalize V. 1, E, 1, N, D, N. Okay? This is the first order correction. Okay, notice that this is just the first step. So the selection of the right states. But once you select the right states, usually, the degeneracy is split. In other words, V now, when acting to first order, already splits the degeneracy. You see this, the final energy for those states is E0 plus E1, E0 plus E1, but all these E1s are different. They are split. At this point, essentially you can continue as before, because now you have nice split degeneracy, and you can essentially apply more standard non-degenerate type of approaches. Okay? So usually in this kind of problems, one stops at this level. Okay? Obviously you can continue, but it's already enough to diagonalize the problem, the perturbation in the degenerate subspace, and find the right starting states. And if you need, you could account for second order and other effects. All right? Sometimes, I must warn you, you calculate the matrix for V, and you get exactly 0. Okay? To first order, the matrix there doesn't split the degeneracy. Okay? This can happen. That means that in order to split the degeneracy, you have to do something more, which is a second order degenerate perturbation theory, which we will not do. Okay? In certain cases, it happens. But in the problems we will do, we don't care about that. Okay? First order will be enough to split the degeneracy. Yep. Splitting the degeneracy, it means that those levels were at the beginning all the same, E0, N. Then I add the perturbation, and this one becomes E0, one becomes E0, N plus E1, N1. This is the state 1. The state 2 becomes E0, N plus E1, N2. Okay? And in general, these are all different. This means splitting the degeneracy. It means that the energy are no longer the same. They're just a little bit different. Okay? And they are different because of the effect of V, of this E1 term. Okay? Because at the beginning, they were just the same. This is the splitting. Okay, so let us see how this works. And the simplest illustration of this is the following. Suppose that your Hamiltonian is p square over 2m minus c square over r. You know this, right? A hydrogen atom. And then you put some electric field on the z-axis, okay? All right, so let us try to see the effect of this electric field, okay? So the spectrum would be the 1s, then again the 2s, and the 3 2p, and then the 3s, 3p, 3d, and so on and so forth, okay, until you get to 0. All right, so you know the energies of this. These are the unperturbed unperturbed states and energies of the hydrogen atom. So I want to see the effect of this electric field, and therefore the first thing I do is, for instance, to first order in perturbation theory. What happens to the ground state, for instance? Well, the ground state is non-degenerate. You might say, okay, it's not non-degenerate. There's spin degeneracy. Well, true. But this operator doesn't care about spin. So to the point that I want to make, this degeneracy is meaningless, okay? So you could just calculate the effect for spin up and for spin down separately, and that would be still fine. In other words, there is no need to write really a 2x2 matrix. If you want, you can do it, but the matrix would be purely diagonal, okay? Okay, good. So what is the effect of this term on this state? So you should calculate what? You should calculate the matrix element of EZ between the 1, 0, 0 state, okay? So psi 1, 0, 0 and psi 1, 0, 0, okay? Remember, the first index is n, the second is L, the third is M, okay? N, L, M, okay? So this is the 1s state. Okay, what is this? How much is this? 0. Usual argument, right? Even, odd, okay? So you see, to first order, this is completely untouched. So in order to calculate what happens to this state, I would need to go to second order and calculate matrix element of Z between this and that, blah, 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 and sum all of them. And what will happen in the end? Something going down, right? So as a function of the electric field, this will just quadratically shift down. Down because the ground state is always shifted down to second order, okay? All right, we don't care really about this. This is not what I wanted to do. What I wanted to do is, for instance, here. Or you can do it even up. Let's do it there. There, I do have 4 states. Once again, you might say, okay, no, there are 8. Yes, but the spin doesn't count. It's always diagonal. So whatever is to the right must come to the left, which means that you can essentially forget about it. All right. So the matrix that I then should write, okay, so what is really this block here in any basis, you see, the basis I have selected is the psi n l m. You might say is not arbitrary. Well, it's not arbitrary, but almost. For instance, who commanded the fact that I should use L and M and not L and X, Y, and Z? I mean, the combinations, the Cartesian combination. I mean, it's a choice in some sense. So let's write the matrix with this arbitrary choice. Let's see what the matrix looks like, and if it is necessary, then we diagonalize it. Okay, so to be, so I'm trying to write the matrix of EAZ in this 4 by 4 subspace. Okay, so here I should write, well, obviously E and the electric field come out, but here I would have, for instance, the matrix element of Z in between. Okay, I order the state in this way. This is state number 1. This is state number 2. This is state number 3. And this is state number 4. In other words, number 1 is the 2s. Number 2 is the state psi 2, 1, 0. Okay? So it has m equals 0, the center one. Then 3 is the plus 1, and 4 is the minus 1. And I do a 4 by 4 matrix. So this is psi 2, 0, 0, psi 2, 0, 0. Okay? So the second column would have the same index here. But now I should put the second state, which according to my ordering is this. Then I would have psi 2, 0, 0, z, psi 2, 1, plus 1, and then I have finally psi 2, 0, 0, z, psi 2, 1, minus 1. Okay? So this is the first row of this matrix. It's 4 by 4. I'm occupying a lot of space, I realize. Probably I might be. Okay, second row, second state, therefore. So here you put psi 2, 1, 0, matrix element with psi 2, 0, 0. The diagonal, 1, 0, z, psi 2, 1, 0. Then the matrix element with the plus 1, and then the matrix element with the minus 1. Okay? Then I would have, well, should I continue? I just start here. Psi 2, 1, plus 1, z, psi 2, 0, 0, and psi 2, 1, minus 1, z, psi 2, 0, 0. Okay? These are the matrix elements you have to calculate. Okay? So you start seeing that this business is already a little bit complicated by the fact that you have certain integrals to evaluate. 16 apparently. We'll have many, I mean, much less than that, because now we use selection rules. So we start arguing. For instance, parity. Let's use parity. Parity is very, very handy. So Z is odd. Therefore, it must connect states only with opposite parity, which means, for instance, that it must connect S and P, but P and P themselves, 0, vanish. Okay? So, for instance, S and P are, so this is, you see, is S, and this is P. So this line, I should take care. This is S, and this is P, and therefore, so, by the way, the matrix is Hermitian, so really you have to calculate half of it, okay? So for instance, this line and this line are just one the star of the other. Okay, this in principle I cannot get rid of, but here, you see, this is the same state, so this must be just 0. And these are still odd, 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 okay? So everything here, okay, is just a 3 by 3 0. Every object is 0. Okay? Which is a nice bonus, right? So, okay, so we have only 8 to calculate. Okay, now let's see. 2s also is even, odd, so this is really 0. Okay, what else? This is in principle possible. indeed, we will see that this is the only one we need. This and the star, which is there. Okay? Let's argue why this and this should be 0 also. Okay? Now, this is slightly more complicated because, in principle, this is even, this is odd, so parity wouldn't help. But here, angular momentum is important. You realize that Z is what? Z is R times the cos of theta. There is no phi dependence. Okay? And therefore, this is invariant by rotation around the z-axis. So therefore, this has angular momentum 0. M is equal to 0. This has angular momentum plus 1 around the z-axis. And therefore, and this has, on the contrary, no angular momentum, so it's 0. So in some sense, you cannot obtain a plus 1 out of two zeros. Okay? I mean, I'm just looking at the phi dependence. This has no phi dependence. This has no phi dependence. This has a phi dependence that is e to the I plus 1 phi. When you take as a star, you have this thing. Okay? How much is this? 0. Okay? So the angular part of the integral kills everything. In other words, somehow you are applying a selection rule relative to the LZ thing. Okay? So this is an eigenstate of LZ, 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 and the calculation is very, very simple. Okay? So by the same argument, this is also 0. So 0, 0, okay? And these are 0. Okay, so let me just write a smaller matrix now. So the one I need is 0, 0. Everything else is 0. Okay? Everything else is 0. So this is a 2 by 2 piece. Everything else is just 0. Okay? I need this element here. Let's call it delta. Okay? So delta, just to write it, is the matrix element, or for instance, let us write 2, 0, 0, z psi 2, 1, 0. Okay? So the one that is here. This in principle is delta star, but you immediately realize that delta, with the choice we made, is perfectly real. Everything here is real. This function here is the R21 times the Y10 spherical harmonics. This is just R times cos theta. And this function here is R20R times the 0, 0 spherical harmonics. Okay? Star if you want, but okay. So you can calculate this. You can calculate this number pretty easily. And one can show, because you have these radial functions, okay? Just to tell you, this is some coefficients times 1 minus r over twice the Bohr radius times e to the minus r over twice the Bohr radius. I'm using now dimension-full variables, okay? So I divide everything by the Bohr radius, and here there's a coefficient that is 1 over square root of 8 pi a Bohr cubed. So this is what really the whole function here is. The function here to the right, including the spherical harmonics, you can really express as follows. 1 over square root of 32 pi a bar cubed times z over ab times e to the minus r over 2ab. Okay, let's see. The 2 here is because we are in the second n equal 2 level. Okay, remember. The a bar appear because we have used now dimensionful things. This is the 2s radial function. This object here is there because of the 1, 0 spherical harmonics. That, if you remember, it's just a cos theta. The 1, 0 is a cos theta, so pretty similar to that. And therefore, it's just z. Okay? So what you have there is z, and what you have here is another z. Okay? So you have to calculate this integral here. And if you do it, the result is not difficult to get. You get minus 3 the Bohr radius. The fact that you should just obtain something times the Bohr radius is obvious. These are, dimensions of a length, right? So you should obtain something proportional to the Bohr radius. The whole calculation reduced, therefore, to calculating that the constant in front is just minus 3. All right? Is this clear enough? I mean, I didn't do the full calculation, but that's in principle what you are supposed to do. So if you do calculate the subject, what you get here is some number, okay? Say minus 3 the Bohr radius, minus 3 the Bohr radius. Okay? Very good. Never mind for the number. You can indeed solve the exercise without even knowing the number. Just call it delta, for instance. So what are you supposed to do now after writing this matrix? You notice that the matrix is not diagonal. Therefore, what you do is you accept the suggestion and you diagonalize this matrix and you select the new states to be the ones that diagonalize the matrix. You have done this exercise many times. A 2 by 2 matrix where you have 0 in the diagonal and some t and t there on delta and delta, okay? You know that there are 2 states, the combination with the plus and the combination with the minus, okay? And they just gain or lose an energy plus or minus delta. Okay, I don't repeat the exercise, but I believe you have done many times, okay? So, yeah. The usual. I mean, these objects here are such that if you normalize with dr r square from 0 to infinity, d theta cos theta from 0 to pi, d phi from 0 to pi, okay, they should, the modulus square of this object should be 1. Okay, 1 equal to psi modulus square. Okay? And indeed, sine theta, obviously. Sine theta. The coefficients here, okay, the 8 pi, they're just the right one to normalize everything, okay? You always have to have the right coefficient in the end to calculate something, because otherwise, if you just have a function that is normalized, your matrix element can be any number, okay? So the thing has to be calculated with a normalized wave function. All right, good. So let us finish this exercise. And so okay, I write here. So you define 2 new states. They are classified still by 2, the n is still 2, but I call them plus or minus, okay? And they are what? They are 1 over square root of 2 the psi 2, 0, 0 plus or minus the psi 2, 1, 0. Okay? So I mix the 2s with the 2p with m equals 0. You know, by the way, that this is also called pz. Okay? This is really the 2pz orbital. And this is the 2s orbital. Okay? So the 0, L equals 0 coincides with the pz. The other two, I mean, are just untouched by anything. So the other two continue to remain +1 and -1, but they are not touched by my perturbation. Therefore, in the spectrum, okay, two of them, for instance, this and that, would keep staying here. These two guys, however, I have to mix them. And I mix them in this way. And by mixing them, one will go up and one will go down. Okay? By how much? By plus delta and minus delta. All right? Now, really, delta is negative, so it's actually kind of the opposite. Okay? So there is the state with the plus really goes down by minus 3 E electric field Bohr radius, and this is the state with the plus. And the state with the minus goes up by plus 3 E electric field Bohr radius. Okay? So linearly with the electric field. Notice, this is quadratic with the electric field. This is a linear object. Okay? Is this clear? This is what I was calling before the splitting of the degeneracy. It's not fully splitted, by the way. Some degeneracy remains, but the electric field splits the degeneracy between the 2s and the 2pz. And you realize, after all, the 2pz is along z, and therefore you essentially make a combination. The 2s is like this, is spherically symmetric. The 2pz is something like this, positive and negative lobe. This is all positive, okay? So what you do is you make two combinations, one with the plus, okay, which somehow makes this part probably bigger, and one with the minus. So the one with the plus is something like this, so there is more wave function, say, in this upper part, and the one with the minus is something on the contrary like that. There's more wave function in the down lobe. If you are puzzled by this, remember, these are functions with certain signs, okay? The S is always positive, but the P changes sign. So if you sum in space, in every point, two functions, the plus and plus sum together, but plus and minus collide, okay? Interfere destructively, okay? So for instance, here and here, the thing is even more positive, but here, the plus and the minus really go, so that's the reason why I draw it smaller, okay? You should calculate. So in any direction, in any, you can plot these functions, but roughly speaking means this. I mean, a more pronounced positive part to the expense of the negative for the plus combination and the opposite for the, okay? And you realize also why then this enjoy the field, because you see they kind of move the probability of finding the electron towards plus z or minus z in a particular way. Okay? Is this clear? Okay. I think I've done something wrong. I do not quite agree with myself. Be a more critical and skeptical about what I said, okay? The one with the plus, I think, is fine, but the one with the minus, no, I'm wrong. The one with the minus really takes this function and changes sign, so it gets a plus here. So no. Okay, the wave function with the minus gets a pronounced positive lobe down. Okay, so try to see physically why one gains and one loses energy. Okay, why don't you think a little bit by, say, plotting and arguing in some way why one is higher in energy and another one gains energy. Okay, so I think this is a useful exercise for understanding a little bit practically the physics of this problem. Mathematically, it's very simple. It's a 2x2 problem with a certain off-diagonal matrix element, which means that you have to mix the two, okay, with the usual plus or minus. But physically, I think it helps. Okay, so I assign to you as an exercise rather than trying to do it here. Okay, so this is called linear Stark effect. Linear because, I mean, well, you see it. Stark because it's electric field, and linear because you see that you split the degeneracy linearly in the electric field. Okay, if there are no questions, I switch to the next and final exercise of this. Yeah.
You say that when they split in the energy, there's still some degeneracy that remains. There's
This too.
okay, you say when they split, you say that okay, some degeneracy
Remains. Yeah. The four states are not all non-degenerate. Two remain degenerate and two just split off, one above and one below.
Okay, and then that change in energy between those states when they split, because we can see there's a difference in the energy.
Yeah.
Does it represent anything?
Of course, it represents. I mean, if you do spectroscopy in a system like this, you would notice, among other things, that by putting the electric field, for instance, the energy between this and this, and the energy between this and this, and the energy between this and that would be different. I don't know if I understood your question, however. I answered some question, but perhaps not yours.
When they split, we can see there's a difference in the energy.
Well, that's the meaning of splitting. I mean, they separate, so there is a difference. Okay? But I don't know, again, if I understood really what you meant. Okay? In absence of electric field, you have these four states like this. You turn on E, so this is epsilon equal to 0. You turn on now epsilon greater than 0, and you have two at the same level here. One above and one below. This is above by plus 3 E epsilon AB, and this is below by minus 3 E epsilon AB. Obviously, this level is still the same, so this is minus a Rydberg over 4, okay? So if you want the energy in absolute terms, would be minus a Rydberg plus that. And this would be minus a Rydberg over 4 minus that. Is this clear now? This is what I call splitting. Now, this is for a fixed E. If I were to draw as a function of E, this would just steadily increase, okay? This splitting. That's the reason why one calls linear Stark effect. All right. Okay. Yeah.
Remaining degeneracy. I know that if we apply the magnetic field, we can split this degeneracy.
But you split another degeneracy. You
Okay. Can the spin orbit split
Absolutely yes. This picture here is in absence of spin orbit. We will immediately now see that indeed this starting point here is not correct. Okay? We'll see next exercise. So this is just for illustration purposes. If you really turn an electric field in a real hydrogen atom, the starting, it really depends how strong is your electric field. If your electric field is very, very small, then you first should make sure you start from the right thing, which is the spin orbit split multiplet. Okay? So just to tell you what we get, these 4 states are really not 4 but 8, because I now draw the spin. What we will get is the following. 4 states out of this 8 end up down, and a multiplet of other 4 states end up higher. Let's see if I remember correctly. No, I'm wrong. They all go down. Sorry. They all go down. But the result would be that one goes, you have a multiplet of 4 states that go down by an amount that is minus 1 over 128 mc square alpha to the 4th. Alpha is the Frank structure constant. Okay? And this, then there are 4 other states like this, which go down by minus 5 over 128 mc square alpha to the 4th. Remember that mc square alpha square is really a Rydberg. Okay, so alternatively, you could write this a Rydberg or a Hartree. I forgot. One should check. Okay, but this is essentially either a Rydberg or a Hartree times alpha square. Okay. I'll check in a second. Never mind. So this is the right situation. Okay. They are not at minus a Rydberg over 4. They are shifted down by a quantity which is pretty small. You see, it's alpha square is 1 over 137 squared. And on top of that, there is also another small coefficient that is 1 over 128 by other sources. And therefore, you realize that this is, not in scale, certainly with the ground state being here. It's a very, very fine splitting of those 8 states into this new object. Okay? So now to calculate really a small electric field on top of this, you should start from here. However, if the electric field is so strong that, it's much larger than these objects, you might also do the exercise by completely neglecting these small splittings and just calculating what we did. In some sense, this is the rule of thumb. First, treat the largest perturbation that you have, and then maybe do small refinements. Okay? Okay, so let us tackle now this problem. It's slightly more complicated now. But the spirit is the same. Spirit is still a perturbation which acts in a degenerate subspace, and I should write a matrix to diagonalize. Now, what are the terms that you need to account for this, to solve this problem? Well, now it's not the electric field that is important, but you have really 3 objects. The first one, they are all relativistic correction. We discussed some of them last time. Is E square over twice mass square c square r to the cube. Remember, we call this object lambda of r last time, okay, times L dot S. This is called spin orbit coupling. H spin orbit, okay? Then there is another object that is minus 1 over twice mc square p square over 2m square. This comes from the kinetic energy. Remember, the relativistic kinetic energy is square root of mc square plus blah, 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 okay? And if you expand, we did it last time, you get relativistic, the non-relativistic term, you get mc square, which we don't care. The non-relativistic term, and then you get this. And there's another object, which is very, very strange looking. And don't ask me where it comes. In other words, I can answer where it comes, but don't ask me for the physics behind, because it's rather obscure to me. I must be honest. Okay? It's a delta function piece. It's called Darwin correction. It comes from the genius of Dirac. Okay? So if you take the Dirac equation and you do consistently the non-relativistic limit, there comes also a piece like that. Rather, I must admit, mysterious to me. I mean, physically mysterious. Not, I mean, mathematically it must be a possible derivation to do. Okay? So this is the Darwin, and this is the kinetic energy correction. Three terms. All these three terms, just a second, are of the same order of magnitude. We estimate last time they are essentially smaller than the Rydberg, which is the scale of this problem, by a constant that is the fine structure constant alpha squared. Okay? So to be definite, there is in this problem there is this constant appearing alpha equal to e squared over h bar c, which is roughly 1 over 137. And you can easily estimate that all these three objects, okay, are smaller than that by alpha squared. Okay? So the average of, say, the spin orbit effect over h0 is essentially alpha squared, and the same for the other three. Okay? Same order of magnitude. For this reason, you cannot go away and say, okay, I just skip this, I don't care about the other. They are the same order of magnitude. Okay? So if you believe only this, then you would get the wrong result. You should add the three of them. Okay. Good. So let us try to set up the problem. Yep.
Does the Darwin correction come from the expression that we did for the square root of the image?
No. No, it's not the square root of the relativistic kinetic energy. That is this. It's something else. I forgot. To be honest, I mean, it's long ago that I saw this derivation. I forgot exactly which is the ingredient. So please do not insist. I will not tell you. Okay? So ask someone else. Okay? I will not tell you. I will not listen. I will not listen. This is it. Okay? This is it. With all the pi's, the two. They are all correct, but unclear. Okay, good. So, one thing to notice is, however, the following. This object is a delta in the origin. So any wave function that is 0 in the origin will not be affected by it. Okay? So you immediately realize that it affects only, for instance, the 2s state. Okay? The 2s is not 0 in the origin, and it feels that. All right? So not the 2p. The 2p doesn't care. Okay. Let us really first look at this piece. Okay? Then to do the exercise finally and correctly, you really have to include all the others. But the main part of what I want to teach you today is this. Okay. So how do you do this exercise? Well, you realize that in order to treat this piece and to write now the matrix, I would have how many states? Well, this really doesn't act on the 2s, because L is 0 for the 2s. Okay? So it acts only on the 2p states. So really I do have the 2p, let's call them. So I have L equal 1, N equal 2, and here I have, for instance, M equal plus 1, 0, and minus 1. Okay? And there are two of them. So I have the spin up, okay, and the spin down. 6 states. They are all coupled by objects like this. Remember, because this has a term that is LZ, SZ, but then there is plus 1/2, L plus, S minus, plus, L minus, S plus. Okay? So this is diagonal, but the other scrambles everything. So in principle, if you go this way, you might end up having a matrix 6 by 6, so even bigger than the one we had before, really full of numbers to calculate. You realize that this is already something that would kill us, so we would not proceed. Okay? So what do? Well, we already know what to do. We know that there are combinations of those states which make the total angular momentum happy. Okay? They are the J equal to 3/2 and the J equal to 1/2 combination. L is still 1, spin is 1/2, but we rather diagonalize J and JZ, obviously. Okay? We constructed explicitly those 6 states, 4 for this and 2 for this. You remember when we did addition of angular momentum. All right? These are just combinations of the previous one with Clebsch-Gordon coefficient. Now, in the total arbitrariness of what states you use, I suggest that this is the best possible choice. Why? Because you realize that L dot S is nothing but J square minus L square minus S square divided by 2. Okay? Because remember, no? J square is just L plus S square, which is L square plus S square plus 2L dot S. So this object here is really a child of these 3 guys. So there. So if you find eigenstate of J square, L square, and S square, they will be automatically eigenstates of L dot S, which means diagonal. Okay? So in this new basis, which is a combination of the previous one, which we constructed last time just for fun, the matrix is diagonal. It is not only diagonal, it's very simple. For instance, the 4 states that are associated to, so J equal to 3/2, and the 2 states associated to J equal to 1/2 will be just, for instance, the value of this thing will be, for 3/2 would be, let's see, so some value here, 3/2 times 3/2 plus 1 minus L square, which is 1 times 1 plus 1, minus S square, which is 1/2 times 1/2 plus 1, okay, divided by 2. Okay, let's calculate this number. So this is, let's see, 3/2 times 5/2, so 15 over 4, minus 2, minus 3/4, divided by 2. So again, how much? Let's insist. So is, if I do it correctly, minus 18 over 4, which is 9 over 2, minus 4 over 2, divided by 2. So this is 5 over help. 5
It's a half.
over 2.
Because
15 over, oh, sorry, it's minus. So this is 12. Sorry, not 18. 12 over 4, which is 12 over 4 is 6 over 2 is 3. 3 minus 2. Okay, now we are closer. 3 minus 2 is 1. Is 1. 1. 1 divided by 2. Oh, very nice. Okay, so this is 1 divided by 2. All right? Did I calculate it correctly? It's a very complicated exercise, you realize. All right. So this one would be a half. A half. A half. Well, a half. A half times what? Now we'll see what is close to here. Here there must be still something, which is after all, this quantity here must be sandwiched between the radial functions, okay? So we'll do that in a second, okay? But the rest, okay, so this thing here is very simple. Now, what about the other two? Well, the other two is an identical calculation, except that rather than having here 3/2, I now have 1/2, okay? So this object immediately, you see, cancels that. And therefore, I just have here minus 2 divided by 2. So minus 1. Minus 1 and minus 1. Again, times some potato here. All right? So now we calculate whatever. And everything else is 0. Okay? So this is quite, a good thing, right? By having done that exercise last time with the construction of the total angular momentum J functions, now we can do in one shot this diagonalization exercise, because when we write in terms of those combinations, the matrix is already diagonal, okay? So you don't have to diagonalize anything. It's done for you. All right. The question is, why did I choose those 6 states? Which ones? The original ones or this? The original ones. Well, the original ones is because I wanted to see what happens to this part of the spectrum, the part that is close to minus Rydberg over 4, the 2s2p states. I wanted to know, to understand what happens if I add this perturbation. Okay, remember, we're trying to do perturbation theory. So learn how to apply small perturbation to a certain problem that we have solved exactly and see the effect. All right? So I want to. Why did I want to do that? Because, I mean, it's your destiny to be suffering with these things. Okay? So this is what I plan to do. So I consider the 6 states. And if I were to write the matrix of the perturbation in this original basis, it would be a 6 by 6 matrix full of numbers. But luckily enough, I remember that I can diagonalize it by just a smart selection of the initial state. This is not L and S eigenstate, but J eigenstates. All right? Total angular momentum eigenstates solve this problem for you. Now, the radial functions that appear here are what? These are p states. So they are R, 2, 1 of R. Okay? So together with the spherical harmonics and spin that I have modified to get, say, this J states, so J equal to 3/2 and Mj equal to whatever, or J equal to 1/2 and Mj equal to plus or minus 1/2, I have a radial function like this. This obviously takes care of the radial part of this lambda of r. So what I should do is to calculate an integral over r squared from 0 to plus infinity of r to 1 star, there's no need really for a star because they are real, times this object, e squared over twice m squared c squared r cubed. Okay? So you need to know this integral, okay? And this integral is the potato I was drawing here, okay? Everywhere, the same integral, by the way, okay? So just calculate one integral. You realize that apart from the universal constant, it's 1 over r squared that you need to calculate between these objects. Now, these integrals are all known. I write it here. Where? I don't know. So, for instance, psi n L m. I write it for the general L m. Okay. 1 over r squared psi n L m equal to, well, dimensions first. Well, this is 1 over a length, so it should be 1 over ball radius cubed, for sure. Then you will have 1 over n cubed, 1 over L, L plus 1/2, L plus 1. Okay? For a general L. For L equal 1, you just calculate this is 1 times 2 times 3/2. Okay? And if n is equal to 2, this is another factor of 8. Okay? So for the one you need, so the psi, the 2, 1, m, then you would have 1 over ball radius cubed, 1 over 8, 1 over 2 times 3/2. So 24, okay? 24, if I'm not mistaken with my algebra, okay? So the potato there is 1 over 24. Well, I can take the potato out, all right? Let's put it out here. It's 1 over 24, the ball radius cubed. Well, not only that, obviously. There is also e squared. There is also 2m squared c squared. Okay? So that's the whole thing. And it takes very little to show that all this ball radius c and mc combine together to give you essentially alpha squared times the Rydberg. Okay? So in principle, you can calculate immediately what happens to the 2p states, the 6 2p states, 6 because of the spin, when you put this perturbation. And what would happen is essentially it happens the following. Let me draw it here. Again, better. So you have, I erase. The 2s doesn't care. The 2p are shifted by minus 1 over 48 m c squared alpha to the fourth, or if you want, alpha squared times the Rydberg. And then there are others that are moved up by plus 1 over 96, the same number, mc squared alpha squared. Let's see, who are these? These are the j equal to 1/2. So it's really 2 of them. And who are these? The j equal to 3/2. So really 4 of them. Okay? Is this clear? So the 6 states organize into a higher j equal to 3/2 multiplet and the lower j equal to 1/2 doublet. Okay? 4 and 2. Now, j equal to 3/2 is moved up because essentially you see L dot S as j squared. So the more is j squared, the more this is positive. The rest is positive. Okay? You see? So the effect is just moving up this and moving down this. The 48 and 96 are just because of this factor here. Okay? Well, maybe I got... Oh, no, it must be because you have everything clear in mind. So mc squared alpha to the fourth is what? The Rydberg alpha square or... What? Okay. Now there is some factors too that I'm missing here. You see. Let's see. Because the 24 I can get from this matrix element. 24 I got. Well, it's not guaranteed that I included this. I mean, you should check all the factors, okay? So please check that written this way, I'm pretty sure. Okay? But I'm not sure that all factors too are perfectly taken care of. No, it's fine. Probably this factor 2 has to be. See, 24 times 2 is 48, I think. Yeah, I think it's probably that factor. And the other is half of it, so there is another factor 2, and this one, the plus 1 over 96. Okay? Well, I think it's fine. Sorry. Now, this is not the whole story, although I don't want to take much longer. Because now you see that the poor 2s is there, still untouched by the spin orbit, because L is equal to 0. But you realize that the 2s is also a j equal to 1/2, right? Because j is equal to L plus s, and if L is equal to 0, this is also j equal to 1/2. So for some reason here you see the j equal to 1/2 coming from the 2s is at this level, and here the j equal to 1/2 coming from the 2p is down. Now this is obviously a problem. It is a problem because you expect that j, which is the total angular momentum, should be, things should become the same with the same angular momentum. I mean, the reasoning behind is kind of invariance, which is probably broken by this object. You see, the same thing is really coming with two slightly different things. Well, the solution of this is that indeed there are still two terms to take care of. So you shouldn't be puzzled by any partial result, because when you put this term, which is there for the 2s, and this term, which is there for the 2s and the 2p, then everything is moved a little bit, and in the end, they are shifted to new states, okay, to new energies that are, so with respect to this initial object, they are shifted by, so these 4 are shifted down by minus 1 over 128 mc square alpha to the 4th, and these 2 are shifted down here by minus 5 over 128 mc square alpha to the 4th, and this object also is shifted down by exactly the same amount. Okay? So the 2s also ends up being down by minus 5 over 128 mc square alpha to the 4th. Okay? Now, these are small things. I am exaggerating here. Okay? So the initial 8 states end up into a j equal to 3/2 higher multiplet, which is shifted down a little bit, and 2j equal to 1/2 other multiplets coming from the 2p and the 2s states, shifted down by minus 5 times that energy. Okay? So this is 5 times bigger than that. Now, all these things, in principle, you have the 1s down here, which is not affected by this thing, can be checked experimentally, okay? Because you can see lines of absorption between the 1s and the, for instance, 2p, and you would notice that there are 2 of them and not just one, and you could measure finally precisely the differences, and you would, in principle, see this thing. Okay? Now, the final part of the exercise requires something that I might ask you to do, which is to take into account this piece and this piece. These are much simpler objects to deal with. The 1 over r is very, very, very simple. I mean, the delta of r. It affects only this by bringing it a little bit up. By how much? By pi h bar square a square over 2m square c square times the wave function in 0. Okay? Because the integral of the wave functions times the perturbation is very simple. It's just the wave function in 0. You know this thing with this coefficient and everything, and you can calculate the shift up in first order in that object. Okay? But there is this other guy, which is a negative sign, which shifts everything now down. So the final destiny is really going down because of a little bit going up by Darwin and a lot of going down by relativistic correction. How do you calculate this thing, by the way? It might seem like a complicated thing, but it's not. Because you know that p squared over 2m is really equal to, you know that p squared minus c squared over r is equal to h0. Okay? So you can write that p squared over 2m is equal to h0 plus e squared over r. Okay? So in order to calculate the sandwich of this object between states, all you need to do, let me erase here the thing, is to essentially do the following. You have h0 plus e squared over r squared, then 1 over 2mc squared with the minus, and you have to take the matrix element of this between any states you want. For instance, psi n l m and psi n l m. Okay, to first order, this is the effect. It's purely diagonal, as you see. It doesn't change L and M. So if you make any combination, for instance, you might say, hey, I made the J combination. Never mind. I mean, the J combination is perfectly fine as the L and M combination. Okay, so you can proceed with any basis. All you see is that there is a term that is H0 squared that you have to consider, but H0 is diagonal on those elements. You know the energy. H0 squared is diagonal with the energy square. Okay? So this is simple. Then there is a term that is H0 E squared over R plus E squared over R H0 plus E squared over R squared. Okay? So how do you take the matrix element of this? Well, this gives you, again, En, the unperturbed energy, the N, squared. So in our case, minus a Rydberg over 4 squared. This will give me the same object, so minus a Rydberg over 4 times the matrix element of E squared over R. This object will give me exactly the same contribution by now acting on the right. Okay, so I have twice that. And finally, I have also to consider a matrix element of E squared over R squared. Okay? So in order to calculate the effect, I would need to do a little bit of algebra, and in particular to have also these two integrals. The integral of 1 over R, matrix element of 1 over R, and the matrix element of 1 over R squared. For the spin orbit, I wrote for you the matrix element of 1 over R cubed. Now you need also these two. They are also calculated. I mean, it's in the books. You can quite easily, you find the expression in the notes. Okay? So you have this number, you have this number, you put together all the ingredients, and you will see the effect that this does. Okay? So, I mean, I admit it's not infinitely fun, but it's very, I mean, gratifying in the end to find numbers that in principle your experimental colleagues might go and try to check precisely. So it's full of 1 over 128, very strange numbers, but in principle they are all coming from very well-controlled ingredients. Okay? So this is what you need to do to really have a better view of the spectrum of this 2S, 2P. Okay? And it's called the fine structure. Fine, again, because those small things, I mean, if you just look from, I mean, in a gross way, you would say, okay, it's just this level, minus Rydberg over 4, which is very degenerate and so on. Then you go closer and you see that it's 4 levels and two others split it down, okay? And in principle, these are measurable. Okay, so this ends our discussion of time-independent perturbation theory. And next week, we will start time-dependent perturbation theory. So when the perturbation now is some field that depends on time, some potential that depends on time, how you calculate the Schrödinger evolution. Okay? You have questions on this? The question is, why does the ground state goes down when you perturb it? First of all, it goes down to second order. I'm not guaranteeing that to any order, okay, so if the perturbation is very big, I cannot tell where the ground state goes, okay? It's not perturbative. But to second order in perturbation theory, to first order, first of all, the ground state might be, doing whatever it wants. The second order formula, however, is very clear. It is the general formula for n is this, minus sum over all m different from n. Then you have the matrix element between of the perturbation between the unperturbed state n and m, modulo square, and E0 m minus E0 n. Okay? Now, if this is for any n, non-degenerate case, if you take n equals 0, this means here you put the ground state unperturbed, and this is n equals 0. So you have to sum over all other states than the unperturbed states, n equals 0, with the matrix element that is certainly positive, divided by a number that is positive, and there is an overall minus sign. So this result is for sure negative. That's it. This is the only thing that is behind. Okay? So to second order is shifted down. All right. Mathematically. Now, maybe your question was why physically? It's a meaningful question. It's probably very, very deep. I would adventure, but probably I would need to think a little bit more, and maybe we can think together. After all, the system knows what to do. Okay, you are perturbing, and he knows how to arrange and really make use of the more freedom to decrease its energy. Okay, in some sense. But I understand this is a very vague thing. There might be some fundamental reason probably behind, but I cannot just think of it right now. Huh? No, it's true for anything. Any object you could think, it goes down. The question might be, why physically? You put an electric field and the ground state quadratically goes down. Good question. I like it, okay? Mathematically, it's very simple. Just perturbation theory, you calculate. Why physically? We all think of it, okay? During the weekend, you keep thinking why physically it must go down, okay? Honestly, I do not have a very, perfectly sharp answer to that. Other questions? Okay, if not, we'll see you next week, okay?